We learn about data in this video. I will talk about attributes and objects, types of data, data quality, and data preprocessing. So what is data? Data is a collection of data objects and attributes. An attribute is a property of an object. You could see an example as the eye color of a person, such as blue, brown, black, etc. Or temperature as a numeric value. Attribute is also known as a variable, field, characteristic, dimension, or feature. A collection of attributes describe an object. An object is also known as record, point, case, sample, entity, or instance. Looking at the example on the right side of the slide, we have 5 attributes on the column, namely TID, refund, virtual status, taxable income, and cheat. And we have 10 objects or 10 rows. Cheat is the target value, the target variable. Attributes carry attribute values. Attribute values basically are numbers or symbols assigned to an attribute. The same attribute can be mapped to different attribute values. For example, height could be measured in feet or meters. Different attributes can be mapped to the same set of values. As an example, attribute values for the ID and for age are both integers. However, properties of attribute can be different than the property of the values used to represent the attribute. Now we talked about types of datasets. A dataset could be a record type, including data metrics, document data, and transaction data. Could be graph type, including World Wide Web and molecular structures. Could be order type, such as spatial data, temporal data, sequential data, and genetic sequential data. Most of the time when we work with a dataset, we work with a collection of records or data objects, and each of which consists of a fixed set of data attributes. Record data is usually stored either in flat files or in relational databases. If the data objects have the same fixed set of numeric attributes, then the data objects can be thought of as points in a multidimensional space, and each dimension represents an attribute. So such a dataset could be represented as an m by n matrix, as an example. And here we have m rows or m objects, and then n columns as n attributes. Another data type in the same group, in the same record data group, is document data. So looking at the example in the slide, each document here as a row is a term vector. Each term is an attribute of the vector. The value of each component is the number of times the term occurs in the document. We define the term frequency as the ratio between the word count divided by the number of words in the document. And this is the frequency of the term. The inverse document frequency is a measure of how much information the word provides, and it is defined as the log of the total number of the documents divided by the total number of documents with a given word. So from there, we define the term frequency inverse document frequency as a product of the term frequency and the inverse document frequency. This help eliminate the natural occurring words and then help select more relevant words. The last data type in the record data group is transaction data. This is a special type of data in which each transaction involves a set of items. So considering transactions at a grocery store, there could be multiple transactions. As an example, here we have 5 different transactions, and each transaction may have multiple items. So for example, transaction 1 may have bread, Coke, and milk. Transaction 2 may have beer and bread, etc. And those transactions could be by multiple different customers. The second group of data is graph data. As an example, we have a generic graph as on the top left corner, a molecule structure, as well as web pages on the right side. And we have links on the web page pointing to other web pages. For example, bibliography point to the second web page. Books points to the third web page, and general data mining point to the fourth web page. The last group of data is order data. The first type in this group is sequence data, such as sequences of transactions. There could be multiple transactions. Each transaction may have multiple elements, and each element may have multiple items. Another example of sequence data is genomic sequence data. Other type of order data includes spatial data. As an example, transactions at different times. Spatial data, where we have examples such as weather data, which could be collected at different geographical locations. Time series data. An example is the stock price over different times. Also, spatial temporal data. As an example, we have average monthly temperatures of land and ocean. Data quality is an important factor in modeling. If you have garbage in, you have garbage out. As an example, a classification model for detecting people who have loan risk is built using poor data. So as a result, some credit-worthy candidates are denied for loans, and more loans are given to individuals that default. Some examples of data quality problems include noise and outliers, wrong data and fake data, missing values and duplicate data. So what is noise? By definition, noise is an extraneous object for objects. It refers to modification of original values of attributes. As an example, when a person talks on the phone, and if the phone is a poor quality phone, the voice could be distorted. When you watch a TV using an outdoor antenna, you could see snow on the television screen. Looking at the figures down below the slides, the first figure on the left side shows the two sine waves of the same magnitude and different frequency. And then in the middle figure, the waves are combined. The figure on the right side shows the combined signal distorted by the noise. We can see that the magnitude and the shape of the signal is distorted. The next to talk about regarding data quality is outliers. So what are outliers? Outliers are basically data objects with characteristics that are considerably different than most of the other data objects in the dataset. As you can see in this example, we have 3 outliers, which are very much far from other data points in the dataset. There may be 2 different cases. The first case is that outliers are noise that interferes with the data analysis. And the second case is that the outliers are the goal of the analysis. For example, with applications such as credit card fraud or intrusion detection. Next, we talked about missing values. Why do we have missing values? In many cases, it is because information is not collected. As an example, when filling forms, people decline to give their age and weight. In some other cases, attributes may not be applicable to all cases. For example, annual income is not applicable to children. How do we handle missing values? One way to handle missing values is to eliminate the data objects, meaning we would delete all the rows with missing values, or variables, meaning we delete the columns. Another option is to estimate missing values using mean, median, and etc. Or we can ignore the missing values. The last item of data quality is duplicate data. A dataset may include data objects that are duplicates or almost duplicates of one another. And this is a big issue when we merge data from multiple different sources. As an example, one same person may have multiple different email addresses. So we may have to merge, combine those duplicates. And this is something that we have to deal with during data cleaning. Next, we talked about data pre-processing. How do we pre-process data before the modeling? We will talk about data aggregation, sampling, discretization, and binarization. Attribute transformation, that transform attributes. Dimensionality reduction, that to reduce number of attributes. Feature subset selection, meaning select a subset of the features, not all the features, and also feature creation. Aggregation is to combine 2 or more attributes, meaning columns, or objects, meaning rows, into a single attribute or object. The purpose is to reduce the number of attributes or objects. To change the scale, for example, cities could be aggregated into regions, states, or countries. For example, objects with store locations in Chicago and more other cities in Illinois could be aggregated into a single row for just the state. Days could be aggregated into weeks, months, or years. The result is that we have more stable data, meaning the aggregated data tends to have less variability. Sampling is the main technique employed for data reduction. is often used for both the preliminary investigation of the data and the final data analysis. Statisticians often sample because obtaining the entire set of data is too expensive or time-consuming. E-determining sampling is typically used because processing the entire set of data is too expensive or time-consuming. When you do sampling, it's important to note that if the sample is representative, then the sample will work just like when you work with the entire data set. A sample is representative if it has the same properties as the original set of data. There are mainly two types of sampling: simple random sampling and stratified sampling. In simple random sampling, the probability of selecting any particular item is equal. There could be sampling without replacement and sampling with replacement. In stratified sampling, the data is split into several partitions and then samples are randomly drawn from each partition. Discretization is a process of converting a continuous attribute into an ordinal attribute, and it could be used in both supervised and unsupervised settings. This figure illustrates unsupervised discretization. We have four groups of points: blue, green, yellow, and red, and two outliers. Basically, the data is just one-dimensional. However, a random wipe component is added to reduce overlap so that we can visualize the points. This is the illustrations of the unsupervised discretization approach. Here we have four groups, and we use equal interval width approach to map the points to the four groups. We can see that the width of this interval is equal to the width of the other interval. So the width of the four intervals are actually equal. Another approach is to use the equal frequency approach, so that we can still map the points to the four groups, and we can see the frequency in this group, in the other groups, are all equal. We could also use k-mean clustering approach. So with this, we have the sum of the distances between the points to each centroid as minimal. And here we still have four groups. We have talked about discretization in the unsupervised settings. How about the supervised settings? Many classification algorithms work best if both independent and dependent variables have just a few values. Let's look at the illustration. So, in the examples on the left, we discretize x and y into three intervals. And in the second example, we discretize x and y both in 5 intervals. So what we see here is that in the two dimensions, The classes of points are well separated. However, but in one dimension, it's not so clear. Also, 5 intervals work better than 3 intervals. If we have more intervals, maybe we don't improve the discretization much. Binarization is the process that maps a continuous or categorical attributes into one or more binary variables. Let's look at an example. We have a categorical attribute that has 5 different values, which are awful, poor, okay, good, and great. We give each of them a value starting from 0, 1, 2, 3 up to 4, and then in one of each columns from h1 to h5. Here we have h1, h2, h3, h4, and h5. He put number 1 in each of the column for each of the categorical value. So for awful, we put 1 in h1. For poor, we put 1 in h2. For okay, we put 1 in h3. For good, we put 1 in h4, and finally for great, we put 1 in h5. So here we have encoded each categorical value by a binary vector. For example, awful is encoded as 1 0 0 0 0, and great is encoded as 0 0 0 0 1, and this is called the one-hot encoding approach. Now we talked about attribute transformation. A transform basically is a mapping that maps the entire set of values of a given attribute to another new set of replacement values. You may have simple functions for transformation, such as x to the k, log of x, e to the x, and absolute value of x. You also have normalization, or also called standardization. Basically, you subtract the means and then divide it by the standard deviation. You also have min-max normalization, such as we subtract the mean and then divide it by the difference between the max and the mean. Dimensionality reduction is to avoid the curse of dimensionality. Basically, we need to reduce the amount of time and memory required by the algorithms. With fewer dimensions, we can visualize the data easily. For example, if we can have just 2 or 3 dimensions, we can visualize data, and it helps eliminate irrelevant features and also reduce noise. There are several techniques, including principal component analysis, single value decompositions, and as well as some other supervised and nonlinear techniques. PCA, or principal component analysis, is popularly used for dimensionality reduction. Its goal is to find a projection that captures the largest amount of variation in the data. As an illustration, we have 2-dimensional data points, and we have 2 axes, h2 and h1. You could see that the data spreads out along the vector E. So if we project the points onto this vector, on this eigen vector, we could then capture the largest amount of variation in data, and then from here we have only 1 dimension left. So from 2 dimension to one dimension. In practice, we may have many multiple different dimensions, and we could reduce to just a few dimensions. Feature subsession is another way to reduce dimensionality of the data, typically for the case of redundant features and irrelevant features. Redundant features duplicate much of the information contained in the other features. For example, when we have purchase price and also in another features we have the amount of sales tax paid. Irrelevant features contains no information for modeling. For example, student ID is irrelevant for predicting GPA of students. Feature creation is to create new attributes that can capture the information better and more efficiently. Basically, we have feature extraction, for example, extracting edges from images. We have feature construction, for example, dividing mass by volume to get the density, and mapping data to the new space using Fourier transform, wavelength transform, PCA, and principal component analysis. ICA has independent component analysis, and more approaches as well.